Hello everyone. In this video, we are going to look at a previous exam paper and we're going to focus on paper 1 physical science for grade 10s. Without any waste of time, we can go through this question paper that I have. This question paper, it was written in Gauteng province and is a 2022 November question paper. I'm going to leave the link on the description of this video. You can download the question paper and you practice with me as I go through the questions. So now the first question that we have here is a multiple choice question. So the instruction says that you are given 4 options and then you have to select the correct one. But remember, you must be able to label your questions, for example, 1.1 and the answer that you select. So the first question says, which of the following physical quantity is not a vector quantity? So first we need to know what is a vector quantity. So a vector quantity is something that has both magnitude and direction. So this means we are looking for a scalar quantity because a scalar quantity only has magnitude. So if we look at the options that we have, the first option, which is A, is distance. And then we know that distance is actually a scalar quantity since it only has magnitude. So the option that we're going to select here is option number A, because A is the one that is not a vector. So if it's not a vector, that means it's a scalar. The other options, B, C, and D, all of them, they are vector quantities. So now the next question, which is 1.2, they say in the equation, change in displacement, initial velocity multiplied by change in time, plus 1/2 acceleration change in time squared, the part of a velocity multiplied by time represents what? Okay, so now if we have velocity multiplying with time, what does this represent? For us to know what does this represent, we need to actually multiply the units of the variables we have. So now we have velocity here. We know that the units for velocity is meters per second. And then we are going to multiply this with the units of time. And then units of time is seconds. So if we multiply this out together, the seconds will cancel out. And then we are going to be left with the units of meter. So now we know that the units meter, it either represents the distance or the displacement, or it can also represent a length. So in this case, we're going to look for something that has a unit of meters. So the first option A, time, that is not correct. Velocity is not correct. Acceleration is not correct. But now the unit for displacement is in meters. So that means the correct option is going to be number D. So 1.2, the answer will be D. So now when we move on to the next question, which is 1.3, they say which of the following is obtained by calculating the gradient of displacement versus time graph. So now when you talk about displacement versus time graph, we are going to have our displacement as the y-axis and the time in the x-axis, because we know time is an independent variable and it is always on the x-axis. So now, if we want a gradient, remember a gradient by definition is the change in the y over the change in the x. So if we look at this position time graph or displacement time graph, we know that the y is change in displacement, and now the x will be the change in time. So what does change in displacement over change in time represent? We know this represents velocity. So this means the gradient of a position time graph, it is actually the velocity, because velocity is the rate of change in displacement. So now the correct answer here, it has to be number B, because velocity is the gradient of displacement time graph. So the correct answer will be B. So now 1.4, it says that in the diagram below, a pendulum pop a mass M is released from point A and swings past point B, C, and D. So they say ignore the effects of air friction. So now, okay, the pendulum starts from A and then goes B, C, and D. So the question says, in which of the following positions will the value of gravitational potential energy of the pendulum bob be the smallest? Okay. So now remember, when you talk about gravitational potential energy, we actually talk about the potential energy which is given as mass multiplied by gravity and height. So now, if height is the highest, therefore we're going to have the high potential energy. But now if height is low, that means if we have the ball at the bottom, that is where we're going to have the less potential energy. So the best point here that will have the smallest potential energy is going to be point C here, because now this one is higher than C, and this one is also higher than that, and D is higher than that. So D, it has the lowest height. So the lowest height has the lowest potential energy, since potential energy is dependent on the height. So the correct answer here we are going to say is C. So now if we move on to 1.5, they say the number of sound vibration per second is, we know that the number of waves in a second, we call that a frequency. Okay, so but now in this case they just represent a wave as sound vibration. So this is the very same thing. Number of sound vibrations per second, we know that is frequency. Okay, so we're going to select number B, which is frequency. So number 1.6, it says that two identical spheres A and B on insulated stands carry charges. The spheres are brought into contact and then separated again. So now, if the charge on sphere A after separation is Q, okay, so remember now the charges were brought together and then separated. So they say now the new charge of A is going to be Q. So if the new charge of A is Q, that means also the new charge of B must be Q. Because remember, if the charges come into contact, there's going to be a sharing of electrons. And then after that, when they separate, they're going to have the same charge, because electrons will be transferred up until they have the same number of electrons. And then when they separate, they will be having the same charge, either a positive or a negative, but they will have the same charge. So now, the question continues to say now, the charge on sphere B after separation is what? It has to be Q. So Q will be what? Will be number B there. So we are going to say 1.C is going to be B, because after separation, the charges will have the same amount of charge. So now 1.7, it says we must consider the circuit below. We can see now we have a battery of 7 volts. And we have this resistor here that is in series, and this is also in series. And then we only have these 3 ones that are in parallel. So they say now, what is the voltage across the parallel resistors? Okay, so remember now, if we have the total voltage of the battery, the total voltage of the battery must be the sum of the voltage in the circuit. But now the voltage of the parallel, it represents like one thing. It is one voltage. So if we have voltage of parallel as 2 here, that means if we say 2 volts plus 1 plus 4, we are going to get 7 volts. So that means the voltage for parallel, it must be 2, because voltage of parallel represents like one voltage. And then we add all the voltages of the series. So now in this case, the voltage of the parallel will be number C, which is 2 volts. So you're going to say now 1.7 is C. So now we have the last question, which is 1.8 on the multiple choice question. They say, which of the following statements best describes resistance in parallel? So now, when we talk about resistance in parallel, remember we talk about a resistance that are connected like this. And then we know when they're in parallel, what is going to happen? The current is going to split. Sometimes they might not have the same current if they're not the same resistance. But we also know that if they're in parallel, they have what? They have the same voltage. So the voltage is the same. They have one voltage, which is the same for both of them. So now we must look for a statement that actually describes what? The resistance that are in parallel. So now if you look at the first statement, they say now adding more resistance in parallel decreases the total current. Okay, so now, okay, this means that we are looking at the relationship of what, of Ohm's law. Remember, Ohm's law says we have a voltage is equivalent to current multiplied by resistance. So now the relationship that we're looking for is between the resistance and the total current. So this means now the voltage must be kept constant. And then now we can clearly see now, if voltage is kept constant, current will be inversely proportional to the resistance, because if you increase current, you must decrease the resistance so that you keep the voltage the same. So current is inversely proportional to the resistance. Consider we have made the voltage to be constant. So now, if we do what? If we increase the resistance of parallel, that means we decrease the total resistance, okay? So if we increase, remember now, the R parallel is 1 over P equals to 1 over R1 plus 1 over R2. Moving on like that. So the more you have resistance, the lower you're going to have what? The total resistance, because this is just a reciprocal. The more you add, the more the total resistance decreases, okay? So now, the more you add a resistance, you are decreasing the total resistance, and therefore, if you decrease the total resistance, this means you increase the current. So the first statement says what? Adding more resistance in parallel decreases the total current. That is incorrect, because when you add resistance in parallel, you are actually decreasing the total resistance. And if you decrease the total resistance, that means you increase the total current. So number A is not correct. So number B, they say now, adding more resistance in parallel decreases the effective resistance. That is correct. Remember, if you add more resistance in parallel, you actually decrease the total resistance. So now the effective resistance means total resistance. So now by adding more resistance in parallel, you are actually decreasing the effective resistance, the total resistance. So the answer for this one is going to be number B. So we don't have to look at C and D. We just know that, okay, the answer here will just be D. I mean B, I'm sorry about that. The answer will be B. So now, when we move on now to go to the questions, the first question that we encounter is question number 2. And then now the 2.1, it says we must determine the term vector. So we know a vector is a physical quantity that has both magnitude and direction. Physical quantity that has both magnitude and direction. You can just write that in full. But now remember, when you define the vector or a scalar, you must include the fact that this is a physical quantity that has both magnitude and direction for a vector. But now for a scalar, you will say it's a physical quantity that has magnitude only. So now 2.2, they say Peter stands at the front door of his house. Avogadro Street is 25 meters away from Peter's front door. So Peter is here at the front door, and the distance of Avogadro Street is 25 meters. So Peter walks to Avogadro Street and back to the front door. So that means he goes there to Avogadro Street, and then he comes back. So now we can see now he will walk 25 meters to get there, and then another 25 meters to come back, okay? So the first question that we encounter, it says that what is the distance that Peter has walked? Okay, that means Peter has walked 25 meters and 25 meters back. That means it is 50 meters. So Peter has walked 50 meters. Remember now, distance is a scalar quantity. We can just add them. We don't have to include the direction. Okay, so now for 2.2.2, they say write down the final displacement of the Peter. So now remember now the displacement is what? It's just the change in position. So remember now Peter, initially it was at the front door, and then he went and he came back, and then he got back to the front door. So that means now there is no change in displacement, because now there is no change in position. He's still on the same position. He went and he came back to the same position. So the displacement is just going to be 0 meters because it seems like Peter is on the same position initially and after. So this will mean that, okay, the final displacement is just going to be 0 meters. So now the last question on this question, which is 2.2.3, they say, is displacement a vector or a scalar quantity? A displacement is a vector quantity because we know that a displacement, it has what? It has both magnitude and direction. Remember, you can write magnitude and direction in full. So you know displacement is a vector quantity. The reason is that it has both magnitude and direction. So now we move on to the next question, which is question number 3. So on question number 3 here, the statement says that car A travels at a speed of 135 kilometers per hour. Okay, so now if we get this kind of a speed like this, 135 kilometers per hour, so we know we can convert this to meters per second because we always work with meters per second. So when you convert this type of a speed, you are going to divide it by 3.6. So to convert this to meters per second, you just divide it by 3.6. So now if you put that in your calculator, 135 divided by 3.6, that will give us a speed of, this is equivalent to 37.5 meters per second. So now this is the speed that was given in meters per second. So they say now the car is traveling at the speed of that approaches a stationary car. Okay, so now they say car A is traveling at this speed and then it is approaching car B. So the driver of car B, notice that car A is approaching him at a very high speed. So the driver of B reacts suddenly by accelerating the car from rest. So that means the car was at rest initially, and then after that it started to accelerate with an acceleration of 1.5 meters per second squared, and then it accelerated for this amount of time, which is 11.5 seconds. After 11.5 seconds, car B continued driving with A. I don't know if the statement is missing or what. Okay, but now let's try to answer the questions. So 3.1, they say what? Convert 135 kilometers per hour to meters per second. We have already done that. Remember now, this thing, you just divided by 3.6. So that means now the velocity is, we have already done that, is 37.5 meters per second. So now 3.2, they say we must determine the velocity of car B while trying to avoid car A. So now we want to determine the velocity of what? Of car B if it is trying to avoid this. Okay, so now remember what we have here, we have the initial velocity of car B as 0 meters per second because it was initially at rest. And then we also have what we call the acceleration, which is given to us as 1.5 meters per second squared. And then we are also given the time that it travels, which is how much? Which is 11.5 seconds. Okay, so now for us to get the final velocity of this, or the speed of car B, we need to use what we call equations of motions. So now, when you use the equations of motions, you have to select a suitable equation of motion. So in this case, we have initial velocity, we have acceleration, we have time. We can just select the first equation of motion, which says final velocity is equivalent to initial velocity plus acceleration multiplied by change in time. So because we are dealing with equations of motions, direction is very much important. So remember now, this car was moving in this direction, so it was accelerating in that direction. And then also the speed will be on the very same direction. We can just say that direction is positive. That means the direction of the velocity will be positive and the direction of the acceleration will be positive. Direction is very much important. So now to get the velocity of car B while trying to avoid car A, we're going to just substitute what we have. we're going to say the final velocity is just going to be initial velocity, which is 0 meters per second, and then the acceleration of the car, which is 1.5, and the time it took or it traveled is 11.5 seconds. So now we can put this in our calculator and get the final velocity of car B. 1.5 times 11.5. So that gives us 17.25 meters per second. Okay, so now remember, now a velocity is what? Is a vector quantity. So in this case, we can just say to the right. We can, because now we can see this thing is going in that direction, and they said we must determine the velocity, and then velocity is a vector quantity, so we must indicate the direction. So it is this much to the right. Remember, you can say right, you can say you can just define it however way you want to, but now we can just say this is to the right. So the next question, which is 3.3, they say how far has car B driven after 11.5 seconds. So now they want the displacement. They want the displacement. How far did the car travel? So now what do we have? We have everything. We have final velocity. We have now initial velocity, time, and acceleration. So we can just select a suitable equation of motion. So now let's just select this equation of motion. Remember, you have the equations of motion on your formula sheet. So we can select the equation of motions that said the change of displacement is equivalent to initial velocity multiplied by change in time. Then you say this is plus 1 over 2 change in time, acceleration change in time squared. Okay, so this is one of the equation of motion you can select. Remember, you can look at this equation of motions on your formula sheet. I'm just taking them from my head, but you don't have to do that because you already have them. So now, like I said, you look at what you have. In this case, we have what? We have the initial velocity, so we can substitute everything there. We have acceleration, we have time, so that means we can get that displacement they're looking for, how far, the distance, okay? So now we can just say, okay, the change in displacement is just going to be how much? Initial velocity is 0, so if this is 0, we can multiply it with time. Already we know that that's going to be 0, but you can just substitute, and then you say now this is 1 over 2. The acceleration is 1.5. So the change in time is 11.5, and then this is squared. So now the change in displacement, we just have to put everything on our calculator. We know 0 multiplied by 11.5 is just 0. So we're going to say 1 over 2 multiplied by 1.5 into 11.5 all squared. So now the answer that we get is 99.19 meters. Okay, so remember now this, they said how far it can be a distance, it's not a displacement, so you can just leave the answer here without the direction. So the last question that we have, which is 3.4, they say now the driver of car A suddenly hits his brakes. Okay, so remember now, when the car is moving and then it hits the brakes, what is going to happen? It is going to continue moving in the right up until it comes to rest. Okay, so that means when the car is slowing down the speed, we say now this car is decelerating. So it's decelerating because it decreases the speed. So now the question says the driver of car A suddenly hits the brakes and managed to stop after what? After 40 meters. So what acceleration does the car A experiences to come to stand still after that 4 seconds? Okay, so now you see now they gave us the time, they gave us the displacement, and we also have the initial velocity, which is the same thing as how much we have calculated it, which is 37.5 meters per second. So what we're going to do, we're going to select a suitable equation of motion that will help us to actually determine the acceleration. Okay, so look at this. We have the time, we have the displacement, we have the initial velocity. If you look at this equation that we used here, it is going to be a suitable equation because we can substitute now the change in displacement, which is 40 meters. We have the initial velocity, which is that much, and we have the time, which is 4 seconds. So if we substitute this time here, we are only left with what? With acceleration as an unknown, and then we will be able to solve the acceleration. So now let's use that equation of motion. We're going to say now the change in displacement is equivalent to initial velocity multiplied by change in time plus 1 over 2 acceleration change in time squared. So we know the displacement when the car hits the bricks. Remember now the displacement is still going to the right, so the displacement will be positive. So you're just going to substitute the displacement as 40, and then the initial velocity was how much? The initial velocity was 37.5, and it was moving to the right, so it's going to be 37.5, and the time is 4 seconds, and then we have 1 over 2. We are looking for acceleration. The time is 4 seconds all squared. So now we can do our math so that we can solve this. This is just going to be 40 minus this whole part there. So we're going to say we have 40 minus 37.5 into 4. So that's going to give us negative 110. And then on this side, we're going to say 1 over 2 into 4 squared. So 1 over 2 into 4 squared, that's going to give us 8a. Then we can divide both sides by 8, both sides by 8. And then the acceleration that we get, it has to be negative because it is a deceleration. So we have negative 110 divided by 8, which is the same thing as negative 13.75 meters per second squared. So now the negative simply means the car is accelerating to the left. So we can just conclude to say now, okay, acceleration is equivalent to 13.75 meters per second squared left. So the car was decelerating. So now when we move on to the next question, on the next question here, we have question number 4. They say study the velocity versus time graph below for motion of a car traveling east. Okay, so this is important. They told us that the car is traveling to east. So if we look at this velocity time graph, what is happening here? We can see now at point A, the car was not moving. It was at rest because the velocity was 0 meters per second. And then it started to move now. It increases its velocity. Okay, it is increasing it. But now if the velocity increases like this, that means now we have the car accelerating and at a constant acceleration. So now the acceleration, to get the acceleration here, we see now the y is velocity and the x is time. So by definition, acceleration is change in velocity over change in time. So this means the gradient of velocity time graph, it is actually the acceleration. So to get the acceleration, we can just use the velocity time graph. And then now, let's say, for example, we wanted to determine the displacement, okay? So to determine the displacement on a velocity time graph, you actually calculate the area under the curve. So let's say, for example, we have now this part here and that part here. So we can get the position from A to B by just calculating the area under the curve. So the area of this shape here we can see is what is a triangle. So we're going to say now the area will be just 1 over 2 base by height. So now the reason why we use the area to calculate the displacement on a velocity time graph is because if you look at the base there, the base that we have is in seconds, and then now the velocity that we have is in meters per second. Meters per second is just meter over seconds. So when you multiply them out, you see now the unit is just going to be meters, and then meters actually represents the displacement. So that is one thing you need to know on the velocity time graph. So with that being said, we can start now to answer the questions. Question 4.1, they say now, define the term acceleration. So remember now, acceleration, you can just define it by this equation, is the rate of change in velocity. So you can just say rate of change in velocity. So 4.2, they say now, use the graph to describe the motion of the car in the following sessions from A to B. Okay, so now I have already explained this. Okay, so question number 4.2.1, from A to B, what is happening? the car is increasing its speed. Okay, it is increasing with speed. And then now, if the car increases its speed, that means it is accelerating. So we can just say, okay, from A to B, the car is increasing the speed. The first point we say now, increasing speed or velocity. And then if it increases the speed, that means it is accelerating. So that means now the car from A to B is accelerating at a constant acceleration. At a constant acceleration. So remember now, you just have a straight line here. And like I said, the gradient of a velocity time graph is actually acceleration. So acceleration is the same throughout there from A to B. Okay, so the speed is increasing from 0 to 20, and then the car is accelerating at the constant acceleration. So now, if we can describe now from C to D, if you look at now 4.2.2, they say we must describe from C to D. So if you look at C to D here, what is happening is that from C to D, the car here, it is having the same velocity. You see now, the car is moving at a constant velocity. So if a car is moving at a constant velocity, that means we don't have acceleration. Acceleration is 0. And you can clearly see now this is just a horizontal line. So that means the gradient of a horizontal line is just a 0. So we can just say now, okay, from C to D, the car will be moving at what? At a constant speed or constant velocity. Constant speed. And then no acceleration. No acceleration. Okay, the last part here is number E, which is 4.2.3. They say now number E to F. E to F here, the velocity is 0. So that means now the car is not moving. So from E to F, car is not moving, it's at rest. And then if it's not moving, therefore no acceleration. Okay, so that is how we can describe those parts of the velocity time graph. So now the next question, which is 4.3, they say calculate the acceleration of the car between D and E. So now remember, like I said, if you look at this graph here, from D to E, we are just having a straight line. So that means the acceleration is the same throughout here from D to E. So the question wants us to calculate the acceleration from D to E. So we know that the acceleration in the velocity time graph is what? Is the gradient of the velocity time graph. So by definition, acceleration is the change in velocity over the change in time. So now, for you to get the acceleration, you can just say, okay, the final velocity minus the initial velocity over final time minus change in time. So this is the same thing as the gradient. Remember, is change in y over change in x. So now, if you look at the coordinates of the final point is E here, the initial point is D. So if you look at the coordinates of the point of E, it is having what? The x coordinate is 60, and then the y coordinate is 0, because the velocity is 0 there. So the velocity is how much? Is just 0 there. But the initial velocity for D is how much? The x value there is 50. Yes, I think it's 50. And then now the time is 50, and the velocity will be 40 there. So now do you see now the initial velocity will just be 40. And the final time that we have is 60, and the initial time is 50. So now if you put this in our calculator, we can get the acceleration. So now the acceleration is just going to be what? Negative 40 all divided by 10. I think 60 divided by minus 50 is 10. So now the acceleration is just going to be negative 4 meters per second squared. Okay, so now you see now from D to E, the car was decreasing the speed. The car is still moving in the east direction, but it was decreasing the speed. So this means the car was decelerating. So it was accelerating in the opposite direction. So now we can just say, okay, this car is accelerating 4 meters per second squared. But now remember, it is moving in the opposite direction. It's accelerating in the opposite direction, which is just going to be, remember the direction was east, so this is just going to be west, because negative will mean west. Okay, so now if we look at now the last question that we have, which is 4.4, they say now in which section A, B, or BC, so A, B here, or BC, let me see, okay, BC is here, okay, is acceleration of the car greatest. Okay, so now if we look at this here, we can clearly see now from B to C, the gradient will be bigger because we have a steeper line. But now from A to B, the gradient will be smaller than B to C. So that means now the acceleration will be highest from B to C. So we are going to say now from B to C. The reason is that it has what? A greater slope. So we can say now this is having a bigger slope, or bigger gradient, or I don't know, you can just explain it anyhow. It's just that this one, it is more steeper than that one. Okay, so now the next question that we have is question number 5. So on question number 5, they say now a roller coaster cut of mass 2 kg is released from rest at point A. So we know that, okay, this is at rest here. So that means the velocity there is 0 meters per second. And then they say what? They say 30 meters above the ground. So the height is given there, 30 meters. And they say now the cart moves along a frictionless surface. So we don't have friction from A, B to C as shown below. So that means now there's no friction. So if there's no friction, that means the mechanical energy is conserved. That means it's conservation of mechanical energy. So the mechanical energy here is the same as there, is the same as there. And then remember, when you talk about mechanical energy, we talk about potential energy plus kinetic energy. So this will be conserved because now we don't have friction. We don't have anything that is affecting the system. So now there's no external forces. So if we now go on and answer 5.1, 5.1 says define the term gravitational potential energy. Okay, so remember now gravitational potential energy is just the energy due to height. So is the energy of an object due to its height, of an object because of its height, due to its height from the ground, Okay, that is what we call gravitational potential energy. Remember that is given as EP is equivalent to mgh. So it is the energy because of the height. We always have mass, we always have gradient. As soon as we put something up, it has potential energy, because if you release it, it will automatically go down. And then now the gravitational energy is just the energy an object has because of what? Because of its height. So now 5.2, they say now prove with calculations the mechanical energy of the cart at point A is 588 joules. So now at point A here, we want to calculate the mechanical energy. So mechanical energy at A is equals to what? Remember, the mechanical energy simply means the potential energy plus the kinetic energy. So now the mechanical energy at A will be equivalent to the potential energy is given as mass multiplied by gravitational acceleration multiplied by height, plus a kinetic energy is 1/2 mass velocity squared. So now we're going to substitute what we have at point A here. So at point A here, we know the mass of the cart there is 2, and the acceleration is always 9.8, and then the height is 30 meters above the ground. But now here, we don't have a kinetic energy because the velocity is 0 meters per second. So if you substitute this as 0, that means the whole thing will be 0 here. So we can just say plus 0, or you can just substitute the mass and substitute the velocity as 0, and then you will see now the answer there will just be 0. So now the mechanical energy at point A will just be how much? Let's just confirm if we get 588. So this is 2 into 9.8 into 30. So the answer that I get, it is 588 joules. So that is how we will prove that. So now 5.3, they say now we must state the law of conservation of mechanical energy in weight. So now remember now the law of conservation of mechanical energy, it simply says the mechanical energy is conserved in an isolated system. So mechanical energy is conserved in an isolated system. So what does this mean? It means what I've just explained. If we don't have any external forces, no friction on the surface, nothing, that means the energy the object has is going to be the same throughout. So the mechanical energy is conserved if we don't have external forces. If we don't have external forces, that means the system is isolated. Isolated system means we don't have any external forces that are influencing the cut or anything that we have. So now 5.4, it says that we must calculate the velocity of the cut when it's at point B. So now remember, we know that the mechanical energy is going to be the same. The mechanical energy at A is 588. So the mechanical energy at B is 588. The mechanical energy at C is 588 because the system is conserved. So the mechanical energy is conserved. I mean, the system is isolated. Okay? So now, to get what? To get the velocity at point B, we're going to use the mechanical energy that we already know. So that means we know the mechanical energy of B because we have the mechanical energy of A. And now the system is isolated. So we're going to say what? The mechanical energy at point B is equals to the potential energy at point B plus the kinetic energy at point B. But now we know that the mechanical energy at point B is the same thing as the mechanical energy at point A. So we're just going to say this is 588. And therefore, the potential energy is just mass, gravity, and height. Kinetic energy is 1/2 mass v squared. So we're going to substitute everything that we know. So the mass of the cut is 2. And now gravity is 9.8. The height is 10 meters above the ground at that point of B. So now the mass is how much? Is 2. And then we are looking for that velocity. So this is just going to be v squared. So if we do the calculations here, we can see now half and 2 will just cancel out. We are just going to be left with a v squared there. But now I'm just going to say 588 on my calculator minus this whole thing, because when you transpose it, it's going to be negative. So now on my calculator, I'll say 588 minus 2 into 9.8 multiplied by 10. So the answer that I get is 392, which is equals to v squared, because this is equals to 1 there. So now for me to get the answer of the velocity, I can just apply the square root on both sides. So if I apply the square root, remember the answer can be plus or minus, but in this case, it's not really that important. We can just say the velocity is 0.80 meters per second. So that will be the velocity of the car at point B. It is still moving in that direction. I don't know what direction is that. Yes, but that is the velocity that we get. Okay, so now if we move on now to 5.5, I mean, now in this case here, you can just say to the right. Yeah, I don't know. We can just say to the right because I don't know specifically what is the direction there. Because the velocity is the vector, so you can just say that is that to the right. And then now 5.5, they ask us what? They say now, how will the mechanical energy of the cut at point C compared with the mechanical energy of the cut at point B? Greater, or remember now, the mechanical energy will be the same because the mechanical energy is conserved. So we can just say, okay, that will be equal to, okay, will be equal to. So why is it equal to? This is because the mechanical energy is conserved. We can just say mechanical energy is conserved, or you can say the system is isolated. Yes, so that is how you would answer question number 5. So now, if we move on to question number 6, what I'm going to do, I'm just going to delete everything because I know this thing here is going to slow down if I don't delete everything that I have here. Let me just quickly highlight it, delete it, so that I can start afresh, and then we have the system that is running perfectly fine. So now on question number 6 here, they say what? The diagram represents the wave with a frequency of 30 hertz moving from left to right. Okay, so this is the wave that we have, and they gave us the frequency is 30 hertz. Okay, so now the first question that we have, they say define the term transverse wave. So we know that a transverse wave is a wave through which the particles of the medium, they move perpendicular to the direction of the wave. So we're just going to say, okay, to define a transverse wave, this is a wave in which the particles of the medium moves, you can write perpendicular inwards, perpendicular to the direction of the wave, or medium of propagation, or you can just say direction of the wave. Okay, so that is what we call a transverse wave. Remember, if you want to define a longitudinal wave, we're just going to say it's a wave in which the particles move parallel to the direction of the wave or to the medium of propagation. So now, the next question, which is 6.2, they say now label the points A, B, and C. So now, if you look at point A here, we know that point A, because is the minimum peak of the wave, this is going to be what we call a trough. This is a trough. Okay, so you're going to say now A is what we call a trough. And then B is going to be what? Where is B? If I look at point B, or point B is here. Remember now, it's from crest to crest. So a length from crest to crest, that is called a wavelength. Remember, a wavelength is just the distance it takes to complete one circle. So if you look at this, it's a quarter of a circle, half of a circle, another quarter of a circle. So that's the wavelength. A distance from crest to crest, or from trough to trough, that's a wavelength. So now we're going to say now, okay, B is the same thing as the wavelength. And then now C here, C, we know this is the point at the top, at the peak, so that is a crest. So we can just say C is crest. Okay, so we are done labeling all that. Okay, so now 6.3, they say how much time has lapsed while the wave moved from R to T, from R to T. Okay, so now let me just clean up here. So if you look at this, from R to T, what is that? That is the period. This time there that it has moved is a period, because now what we have here is a time it takes to complete one wave, which is 1 second. So you see now this is half of a circle, another half of a circle. So the time here will be the period. So now this question wants us to determine the period, how much time to move from R to T. And then we can determine the period because we have the frequency. We can say period is equivalent to 1 over frequency. So we can just say the period is 1 over 30, and then we can get that in our calculator. So 1 over 30 is the same thing as 0.03 seconds. So now we have 6.4. 6.4, they say now, a point R, S on the wave in phase. Explain your answer. Okay, so now let's look at point R and S. R is here, S is here. Okay, so now when you talk about the points that are in phase or the points that are out of phase, we look at the direction through which that point is going. So if we look at the point of R here, the point of R, it is going to go up as the wave is going to the right. The point is going to go up. But now, if you look at the point of S, the point of S is going to go down. So now, point R and S are out of phase. So they are not in phase. So we are going to say what? No, they are not in phase. No, they are not in phase. Why are they not in phase? It's because now they have different directions. Okay, I don't know how you can define that with explanation, but you can just say, okay, when point R, when the wave goes to the right, when the wave moves, when the wave moves, point R is going up, is going up, and point S is going down. Yes. So that is why they are out of phase. They are not in phase, they are out of phase. So that is how you can answer that question there. So now the next question that we have, which is question number 7. On question number 7, they say we have two identical insulated spheres, sphere A, sphere B. They are subtended by a light inexchangeable string from a ceiling are held at a distance apart, as shown below. So they say now sphere A carries a charge of 2 nanocoulombs, while sphere B is neutral. Okay, so now the first question that we have, they say what? 7.1. They say now we must explain what is meant by a neutral charge. Okay, so now if we talk about a neutral charge, we simply talk about a charge through which the number of protons and electrons are the same. So we can just say, okay, number of electrons and protons are the same. That is what is meant by neutral charge. A neutral charge does not mean you don't have any charges. Remember now, in each and every atom, in each and everything in the world, we have charges. Okay, we have what we call electrons and protons. So now if we have 2 protons and 2 electrons, the overall charge of this is just going to be 0. So it's going to be neutral because the charge is balanced. But now if you start to have excess of a charge, that is when you get a negative charge, or when you have excess of protons, that is when you're going to have what? A positive charge, like here. So you can see here we have excess of protons. That means protons are more than electrons in this case. Okay, so now that is how we can explain a neutral charge. So we have a statement that says sphere A is brought near to a neutral sphere of B, and spheres are allowed to charge each other. Immediately after touching, sphere B moves away from sphere A. Sphere B now has an excess of 20 electrons. Okay, so now after they move together, they separate. So this one will have what? Will have excess of 20 electrons when they're separated. Okay, so we know that when they come together, there's going to be a transfer of electrons. Remember, the electrons was 0 here. I mean, not 0, they were balanced with protons. So the excess was 0. So now electrons were transferred, or whatever that was done. And then at the end, this sphere of B here will have excess of electrons, which is 20 electrons. That's what the question says. So now, 7.2, they say now, state the principle of a conservation of charge in weights. So a conservation of charge, this means what is the net charge of an isolated system remains constant during a physical process. So that means now the net charge is just going to be the same. Okay, you can just say it in simple ways. You're going to say now, okay, the net charge is conserved. conserved or constant in an isolated system. Conserved in an isolated system. Isolated system. Yes, please don't mind my spelling. You just get the content. The spelling we'll talk about it later. Okay, isolated system. Okay, so you can just say now, okay, conservation of charge is just that the net charge in an isolated system is conserved. Remember now, that's the very same thing that you use for mechanical energy. Mechanical energy in an isolated system is conserved. If something is conserved, you can just use those words. In an isolated system is conserved. So now, 7.3, they say briefly explain how the neutral sphere is attracted to the sphere of A. So now remember now what is happening is that the sphere of A, it is having excess of proton. That means it is positively charged. Like I said, this neutral charge here, it is not like it does not have charges. It has positive and negative charges that are balanced. So now what is going to happen is that because we have a positive charge here, this positive charge will influence this charge here. It is going to be attracted to what? To the negative charge there. It's going to influence it. And then when it influences it, it's going to cause this thing here to be slightly positive, or whatever that is going to happen, slightly positive. Okay, so now because of this force that is attracting the negative charge, we're going to have what you call this concept is called polarization. So because of polarization, at the negative charge here of the neutral charge, it is going to go closer to what? To the charge of A here. So the negative charge will go closer to the charge of A because it wants to be attracted to this positive one. So now at the end, this will be partially positive. So now due to polarization, what is going to happen? The negative charge, negative electron or charge, negative charge in sphere B will be attracted to A, will be attracted to charge A. And then now the charge of B will now be slightly positive, because now you see now it's like the negative is moving away from it. So the charge of B, the B charge will slightly be positive, will slightly be positive. That is what will happen, and that is why those spheres they will come into contact. They will attract each other. Okay, it's because there is a positive charge that will attract the negative charge closer to the sphere of A, and then now the sphere of B will be slightly positive. Okay, so that is the concept. So the sphere of B will be moving closer to A, as A is actually pulling that negative charge. So now 7.4, they say calculate the magnitude of the charge of sphere B. So remember now, on the sphere of B, they said it has excess of 20 electrons. So now if we have number of electrons, we can calculate the charge by using, we know the number of electrons is the same thing as a charge divided by amount of charge in one electron. So now we have 20 electrons, and then we are looking for a charge. We can remember this is a constant here. We can just take it out from the back of the question paper. We can just say that is actually negative 1.6 times 10 to the power of negative 18 from what? From the back of your formula sheet. And then when you cross multiply out here, you're going to have a charge. Okay, so now in this case, we're not actually sure if the charge is positive or negative, because this negative electron here, it can be what? It can be negative, it can be positive. So in this case, we just substituted it from the formula sheet. But my advice is just for you to just substitute it as positive. And then you determine whether the charge is positive or negative by an analysis. So now we're going to have what? 20 electrons multiplied with 20 multiplied with 1.6 times 10 to the power of negative 18. So that is 3.2 times 10 to the power of negative 17 coulombs. So now the charge is going to be what? It's going to be negative because it is having excess of electrons. You see now they said it has excess of electrons. That means it has excess of electrons. Therefore, the charge will be negative. Okay, so we're going to say now, okay, the charge here is negative 3.2 times 10 to the power of negative 17 coulombs. The reason why I don't want you to substitute the negative here, because sometimes the electrons might be lost. And then if you put the negative, you will make the charge as if it's negative, and of which the charge will be positive. So you just have to look at if ever there is excess of charges, excess of electrons or excess of protons, to actually assign a charge a positive or a negative. So now the last question that we have, which is 7.5, they say calculate the charge on each sphere after they separated. Okay, so now we have the charge of B and we have the charge of A, which was that. So now remember now, when you calculate the charge after contact, we're going to use what we call the new charge after contact. And the new charge is just the average of the charges. So we're going to say the charge after contact, which is new charge, is equals to charge of A plus charge of B divided by 2. So now the new charge that we have is going to be the charge of A is how much? Is actually positive 2 times 10 to the power. Remember, n means nano. Nano is negative 9. And then we have the charge of B, which is negative 3.2 times 10 to the power of negative 17, all divided by 2. So now the new charge that we get is going to be, let's say, 2 times 10 to the power of 9 minus 3.2 times 10 to the power of negative 17, all divided by 2. So now the charge that we get is actually 1 times 10 to the power of 9 coulombs. Okay, so on my calculator I punched positive 9 there, so let me just use negative 9 there. So that's my bad. I'm sorry about that. That's not the correct answer. So if I put negative there, I get a 9.99 times 10 to the power of negative 10 coulombs. So that is what we get as our answer there. So now the next question, which is our last question, question number 8, it says that in the circuit diagram below, each cell has a voltage of 1.5 volts. Okay, so now if we look at this here, how many cells do we have? We have 1, 2, 3, 4, 5 cells. Okay, so that means now if we have 5 cells, this will mean now, okay, each cell it is having 1.5. Okay, let me just confirm. This is 1 here, this is 2, 3, 4, 5. Yes, that's 5. So now to get the voltage of 1, we're just going to say this is 1.5 times 5, because we have 5 cells there. So to get that voltage of 1, just going to be 1.5 times 5, which means the voltage of the battery is actually 7.5 volts. Okay, 1.5 here, that means it's the voltage of the cell. They say each cell is that. Okay, so now they say use the diagram to answer the questions that follows. So now we can see now this is in series here, so the total current will pass here. But now this is in parallel, the total current will split, but this will have a 1 voltage, and then this will have 1 voltage. So the voltage of this plus the voltage of parallel, it must give us the total voltage. So now if we start to answer 8.1, they say now what is the voltage on reading 1? Okay, we have already done that. The voltage on reading 1, because this is the voltage on the battery, and the battery has 5 cells. Each cell is 1.5 volts. That means you're going to say 1.5 multiplied by 5 cells. Therefore, the voltage of the battery is just 7.5 volts. So now 8.2, they say calculate the following, 8.2.1, the total resistance of the circuits. Okay, so now remember, now the total resistance is the sum of the resistance in series plus the sum of resistance in parallel. So now remember, to identify which resistance are in series and which resistance are in parallel, we just look at the flow of the current. So as you see now, the current comes from the battery. The total current will pass through this here. So that means this one is in series. And then now when the current gets here, it is going to split. So all these things here are in parallel. So now we can confirm that, okay, the total of series is just going to be 2.67 ohms. But now to get the total of parallel, we use the equation for parallel resistance, which is 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So now to get the R parallel, we will substitute our resistance that are in parallel, of which is these three resistance. So the first resistance is what? 1 over 6 plus 1 over 4 plus 1 over 3. So now if we put all this in our calculator, 1 over 6 plus 1 over 4 plus 1 over 3, what we get is 3 over 4. But now remember, this is not the R parallel. So we just have to do the reciprocal. So that means this will move to the top, that will move to the bottom. So now we're going to have the R parallel being equivalent to how much? To 4 over 3 ohms. So that is our R parallel. So now we have the R parallel and the R series. So therefore we can get the total current. The total resistance. So you're going to say now the total resistance, we just add them. The R series is 2.67 plus the R parallel, which is 4 over 3. So now the total resistance will be the same thing as 2.67 plus 4.3, 4 over 3, which is the same thing as 4 ohms. So this is 4.400, so that's going to be 4 ohms. So the total resistance is just 4 ohms. So now when we move on to the next question, which is 8.2.2, they say we must calculate the reading on ammeter 1. So ammeter 1 here, it actually indicates the total current because it's the current that comes straight from the battery. So now, if you're looking for the total current, we can say now the total current, we can find it by using what we call the total voltage is equivalent to the total current multiplied by the total resistance. This is what we call Ohm's law. So remember, we have the voltage of the battery, which was 7.5 when you multiply each cells. So now we have already calculated the total current. The total resistance. So therefore, we can easily calculate the total current, which is the current in A1. So we can say the total voltage is 7.5. So we are looking for the total current. Therefore, the total resistance is calculated to be 4. So we can divide both sides by 2 and get the total current to be how much? We have 7.5 all divided by 4. And the answer that we get is 1.88 amps. So that's the current or the total current that we get. We can just say a current in A1 is 1.88 amps because A1 represents the total current. Okay, so now the next question, which is 8.2.3, they say now we must calculate the reading on V2. So V2 is this one here. Okay, so now remember, now if you look at the V2 here, we know the current that is going to pass here is the total current, which is 1.88. So we have the current, we have the resistance. That means we can determine the V2. So we're going to say now, okay, the V2 is the same thing as the current that will pass through resistor 2 and multiply by resistor 2. So we can just use that equation. So now we know the voltage at V2 is what we are looking for. So this is going to be V2. And the current that passes through there is the total current, which is 1.88. And therefore the resistance there is just 2.67 ohms. So to get the total, the voltage of 2, we're going to say 1.88 multiplied by 2.67, which will give us 5.02 volts. So 5.02 volts, that is our voltage of V2. So now the last question of this whole paper, they say now we must determine the magnitude of the charge that flows through ammeter 1 in 6 minutes. So now if we want to calculate the charge if we have the current, we can use the equation for the charge. Okay, so we know that a current by definition is the rate of flow of charge. So this is the equation for current. Current is charge over time. So now we know the current in A1 is 1.88, and then they gave us the time, which is 6 minutes. But now 6 minutes, we must make it to be in seconds. So that means we must multiply it by what? 60 minutes multiplied by 60. That will give us seconds. Okay, so now we're going to substitute the current that we have. The current that we have, which is at A1, is 1.88. And then we are looking for the charge. So now the time is 6 minutes. But now 6 minutes, we have to convert it to seconds. So that means we must multiply it with 60. So now to get the charge here, we just cross multiply. We say 1.88 multiplied with 6 times 60. And the answer that we get is 676.8 coulombs. And that will be the charge that we have. Okay, that is all for this video. Thank you very much.